Okay. Good morning to our series of understanding Higgs mechanism. The last class we end up here. We started with spontaneous breaking. We have the Higgs field, Lagrangian for the Higgs field is on the board here. This is the kinetic energy part, this is the potential energy part, and this is due to the potential energy without interaction, and this comes out due to the self-interaction of the Higgs field. So it's a 5 power 4 this comes. And when we have taken mu square, the mass term comes from here, because we know that this is in the kinetic energy, this mass half kx square k is equal to m. In the particle case, the kinetic energy is equal to half m omega square x square. So that's why the mass comes from here. The under root of mu, mu will be the mass term. So if you take the mass as positive, it means the potential is a function of phi square and plus 5 power 4 square, and the phi square, then V is a function of phi square plus 5 power 4. And you plot the graph of the variation of the potential with the function phi. This gives you phi square type graph, this phi 4 type, and if you add up, this will again a parabola. So this we have done for if you take mu as positive and this as a scalar number. Okay. Now if you take mu as negative and this again the scalar number, it means the graph for this potential will be upside, instead of parabola upside, it will be upward, like this parabola will be. And for this the parabola is, and if you sum up both, you will get the potential energy curve like this, which is here shown here. So in this case we have the potential, and this is the zero potential zero, this is the potential energy. It means the potential energy is not settled here at 0. At phi is equal to 0, the potential energy is, although it's 0, but it's not less than 0. The potential energy settles here. The minimum value of the potential is here. It's not at 0. So it means we have two values of the potential, minimum potential. If you take mu square as negative and lambda as positive scalar, then we get this settled type graph, variation of the potential. In which case we get the minimum potential at two different points of fields, not at zero field. And if you want to find the minimum values of this field, to find the minimum value of the potential, you just differentiate this potential part with respect to phi and equate it to 0, and you will get two values of the minimum potential. This is at this point and at this point. This we have discussed in the last class. So now from today, today, we will, instead of we just shift the zero value of the field. We just now continuing with our Saddle type potential. and this is the less than 0, and this is 5 feet here. So this gives you the variation of the potential energy with the field when mu square is negative and lambda is positive scalar. Now, when we can, instead of taking a 0 value of the field here, 5, 0 here, why not we shift the 0 from here, where the potential is minimum. This is just simply because you just shifting the reference will not change the physics. So why not we take one of the minimum potential as our reference. So we can take one of the minimum value. Value of the potential as our reference from here to here. This is the value of V and this is the value from V function of 5 at 0 to the potential V of 5 at V. And let us denote the new field. Let us take this as a reference. Okay. So we start the field. Assume that this field is 0 here, and it is here. It is, and so we let the new field is denoted as eta. So the value of eta is, in that case, if you take this as eta field here instead of pi field, eta will be 0 here, it will be minus V here, minus V here, and it's minus 2V. So let us denote the new field by that is where eta is 0, phi was V here. So eta is phi minus eta will be 0, phi will be equal to. Now we can imagine in this case, we can imagine that this is just a potential like this for the eta field. Means we can assume this is just like a cup, particle vibrating in a cup. So it's just like a particle, we can assume that it is just like a particle vibrating in this cup, in this bowl. So now we can imagine a real mass vibrating about eta is equal to 0, but the graph is not symmetric here about eta is equal to 0. It has spontaneously so we can imagine a real mass to be vibrating about eta is equal to 0. But at the cost of breaking symmetry, but the graph is not symmetric about eta is equal to 0. Not symmetric about it as well. Suppose then it means symmetric is automatically broken. Now let us substitute in our Lagrangian for the Higgs field the value of eta instead of just this one or this thing. We do not need these things, so I'm just removing these. Now we have the Lagrangian for the Higgs field. Half mu square half del mu phi square minus half mu square phi square plus 1 by 4 lambda. Now since we have shifted the our axis reference, so in that case eta was of phi minus, or we can write v as phi plus eta. Sorry, phi, you want to find phi as eta plus. So instead of writing taking phi square as our field, we substitute the value of phi as in terms of eta, where v is the constant value of the field where the potential is minimum. So this value is constant, and this is the field has now shifted from phi to eta. So we substitute here phi plus eta plus phi, eta plus say v minus half mu square eta plus b plus 1 by 4 lambda eta plus b. where V is the constant value of the field phi, which is minimum potential. So the derivative of this constant will be 0, and you will left with the kinetic energy part will remain half del mu this is the kinetic energy part. V is constant, so derivative of V with respect to space and time will be 0, so it's good. Now we have half mu square. So beta square plus p square plus 2 beta v, okay, plus 1 by 4 lambda 4 plus 4 factor v plus 6 beta square v square plus 4 beta v cube plus v to the power 4. This is expanded in the binomial expansion term, so you will get this one. Now, we have taken mu square as negative, and the mass term, the mod of mu was lambda v square. So the value of mu square is minus c will be here, and that value is, its mod is lambda v square. Substitute these values here and you will get so I'm just working out on this side because this is already, this has nothing to do with, no change here. Okay, so this will make you mu square. If you take this bracket, or you take this as this bracket. So this is yes. If you open this bracket, this parenthesis, and substitute the value of mu square as negative, this will become positive. So this will be positive half. And the value of mu square is lambda v square. So it is lambda v square. And it's minus sign here. So minus comes here. Minus 1 by 4 lambda. This whole thing. Beta 4 plus 4 beta cube v plus 4 plus 6 beta square v square plus 4 beta v cube plus v. Now open the bracket, you will see that something will cancel out. So 1 by 2 lambda v square beta square plus 1 by 2 lambda v to the power lambda v power 4 plus 1 by 2 cancels out. It's lambda eta b cube. Okay, lambda eta b cube, 2 cancels out. Now this here minus 1 by 4 lambda eta power minus 4 cancels out. We are left with lambda eta cube minus lambda eta cube. Okay. Okay. Now 3 by 2. 6 by 4 means 3 by 2 lambda eta square. Now minus 1 by 4 is 4 cancels out. We are left with lambda eta 9 minus lambda b to the power 4. So this cancels with this. And here this part and this part. Okay, so it's plus 1 by 2 minus 3 by 2. It means it is minus 1. Okay. And what about lambda b to the power 4? Lambda b to the power 4 here, lambda b to the power 4 here. 1 by 4 plus 1 by 2, so plus 1 by 4 lambda b to the power 4 plus half lambda b. So we just write, we will take half integral g part plus minus here, just arrange lambda b square here, lambda b square test lambda b square test plus half minus 3 by 2, that is means minus, so it's minus here. Now lambda eta b cube lambda eta cube lambda b cube term, square term, then cube term, and then the fourth power term lambda eta, it's minus here, so minus taken out, so it will be plus 1 by 4 lambda. Okay, and the last one is this one and this one. So it's a plus half, it's a minus 1 by 4, so minus, it means plus 1 by 4 is lambda b to the power 4 is, it will be 1 by 4 minus 1 by half. So it will be lambda e to the power 4 by 4 plus but this is a constant term. Lambda is a scalar constant. B is the minimum potential in the phi field. This is a constant value. So this has nothing to do with, this can be omitted. And this is the Lagrangian of the eta field, where this is the kinetic energy part and this is the potential energy part. And this is the potential energy, and this is due to the self-interaction term on eta field. So these two this is the kinetic energy of eta field. This is the potential energy of the eta field without interaction, without self-interaction, and this is the interaction of the eta fields, and this is also the interaction of the eta fields. So these are self-interaction terms. Self-interaction of eta field. So now if we ignore this self-interaction part, because the cubic part of eta field and quartic part of the eta field gives you the self-interaction term, and if you ignore this self-interaction term, the Lagrangian for the eta field will be this, the kinetic energy part, this is the potential energy part, and this will be the mass term here. So the Lagrangian for ignoring, suppose if we ignore the self-interaction term, if we ignore the self-interaction term of eta field, the Lagrangian will be half minus lambda d square. So this is the potential energy part, and the mass term here will be mass term is lambda d square, which is real. This lambda is the scalar number which we have considered as this is also this. So these are all real part. So the mass in this case comes out to be a real, and is we assume the field potential field like this, like saddle type. And take the value of field starts here, eta is equal to 0, eta rises, and this is the potential energy part. The mass of the field quanta here is lambda b square, which is a real value. It means as if it is the real mass is oscillating in this cup, this potential field. Now, when we have taken the Lagrangian for phi field, we were having lambda mu phi square minus half mu square phi square, and assume here again mass as positive. If in that case this was the mass mass was given by the square root of this. That is the mass. So if you compare, and in that case, this the if you assume mu square as positive, the potential energy will vary like a particle in a ball here. For mu as positive, it was just like this. We have to consider, we have worked out this one. This is the potential energy part, and this is the field for pi field. And in that case, the mass was given by the square root of mu. So mu square, it's mass is given by mu only. So the mass term is given by mu. So if you compare this mass with this, and if you compare from this field and mass from this field, comparing 1 and 2, we get the mass is half mu square as lambda mu square, and mu square is then 2 times lambda v square, and mass of this will be square root of this. So the mass of the Higgs field, mass of the Higgs, because this is the Higgs field, and the mass which originates here due to the excitation of the field is the mass of the Higgs field. So the mass of the Higgs field will be under root 2 lambda v square, which is under root 2 times the mass of this field. So the mass of the Higgs field is under root 2 times the mass of the field before symmetry breaking. After symmetry breaking, we have the mass of the Higgs field as root 2 times the mass before symmetry breaking. From the experiment, we found that the mass of the Higgs experimentally comes out to be 125 GeV from 2012 experiments at sun. Now it is worth mentioning that physics of this new field, means eta field, would not be different to the phi field, because merely shifting the field by a constant does not change the physics, because we have just shifted, not change the physics. The actual Higgs field is not zero everywhere in space. It still has values plus v and minus v. Using eta is simply to understand the mathematics. We have just shifted just to understand the mathematics. The field phi settles at the value of phi is equal to 0, phi plus minus. This is the phi field and this is theta field. So that just merely shifting the reference will not change the physics, and still we have the two values of the phi field, plus and minus. So we have two values which corresponds to the minimum values. In the language of physics, this is called degeneracy. The field could equally settle to the value of plus v or minus v. There is no preference over plus v to minus v or minus v to plus v. So the question is that could we have different values of v at different positions? Somewhere it's a plus v or minus v. Whether we should take plus v or minus v, or at random at somewhere plus v and minus v. So we can because if we choose different values of the field at different positions, the kinetic energy will be different, very fluctuating. So if we choose the values of plus v at some point and minus v at some point, this amounts to a difference in the field by 2v. This amounts to a difference in the phi field by 2v. So the kinetic energy part phi. This change in the phi is very large. So the kinetic energy part is very large, but the potential energy is still at its minimum. So the only way to really minimize the energy at every point space is to come to the same decision, either plus v or minus v. Because in that case, if you assume that it's the kinetic energy minus potential energy plus 1 by 4 lambda phi. So if we take different values of v at different positions, then the change in the v value at 2 points from plus v to minus v will change with this one, and then the kinetic energy part will be very large, and we want the proportionality to be minimized. So it's judicious to take one value of the v, either plus v or minus v. The Higgs field is a scalar field, simply number, no direction is involved. It has a unique property that it has negative mu square. That would mean imaginary mass, but the symmetry breaks spontaneously, which gives real mass values. Real mass values is given by 2 times the mu. So Higgs field is not zero throughout the space, but has a value. Higgs field has values here. It's not zero, still at the minimum position there is some values of the Higgs field, and this field value is given by V is equal to mass of the Higgs, mass divided by 2 and lambda, because the mass of the Higgs was, it's actually under root 2 lambda v square. So the value of v will be given by mass of the Higgs divided by under root 2 lambda. Okay. So it means the Higgs field is permeated throughout, where the potential is, even though the potential is minimum, still there is some Higgs field remains. So this is about, in the next class we will see that this Higgs field, we have taken Higgs field just like one dimension, but it's not a real values. But actually Higgs is a complex number. Higgs field is a complex number. So the next class we will do the take the phi as a Higgs as a complex quantity. Okay.